Swayam Prabha. Digital India. Educated India.
With the different parts of the modules. And we can start with essentially learning objectives here for this for the module 1, where we're looking at the fundamentals. So we're going to talk about basic amplification factors, an American practice emphasis. I'm sure you can ask me some questions, and we can relate a bit with how some of the similar factors work in the Indian code. I'm going to focus mainly into, okay, here's, I think the AISC provisions have things set up fairly well for that, for what they're good for. But there's limits, so we'll kind of see some aspects of that as we're studying a few things. We'll look at how we can go about, how do we make sure that we're calculating accurate second-order elastic moments, particularly if you use a fairly coarse discretization of the structure. How do you make sure that you need, in design, we need the maximum second-order elastic moment along the length of the member. Okay, let's make sure we have an adequate calculation of that. B2 is an amplifier that we use for that's a notation for side sway in the AISC standard. So we'll look at some fundamentals behind that, some very closely related things in the Indian standard. Again, I'm not going to try to lecture you too much about the Indian standard, but I think we'll be able to see some very definite connections there with some of those things. And then there's various ways to apply these side sway amplifiers, and some ways can work well in certain contexts and then can be very dangerous in other contexts. So that's going to be an important takeaway. We'll look to, again, understand in terms of accuracy how many elements do we need per member for a general purpose type of structural analysis. That's what we'll be applying in Consteel. And particularly there's some gotchas when it comes to use of general purpose software with torsional stiffness approximations. With most of the software out there, Consteel basically surmounts all that because it's based entirely through, everything they do is based on a 14 degree of freedom element with 3 translations, 3 rotations, and warping, and a warping degree of freedom at each node. So that allows us to, with thin-walled open sections, to basically capture the thin-walled open section beam theory behavior quite well, and that's the basis of our code provisions for a lot of the things we do. All right, so there's topics, and you'll see the topic numbers kind of scattered through some of the different lectures, and so you'll be able to know that we're coming back to here for certain things. We're going to focus on topic 1.1 here for the first session. We'll take a break and talk a bit about 1.2, and then I want us to spend some time. Hopefully, I can have you in a good place where you can see how powerful some of the Consteel software is today. We'll just do some very basic things with it, and we'll continue to work with it further as we move through the course. In terms of source materials, I've got a lot of the materials here are from the AISC Construction Manual 16th edition, which is 2022 edition. That's the gold book there. But also, I was fortunate to be involved with some other really smart engineers in several design guides. Design Guide 25 there in the middle, and Design Guide 28 AISC and AISC MBMA guides that AISC provides in U.S. practice. And of course, I've been looking a lot at the Indian standard to try to tie in with that where it may be useful. All right, so topic 1.1. Let's start with the most basic problem you can possibly talk about in terms of second-order effects. We've got a member that's subjected to axial compression and subjected to equal and opposite bending moments, so it's in uniform primary bending. But, of course, we have a deflection of the member in bending, and because of the axial compression, the bending is increased. That's what we call our P small delta effects here. P small delta effects because the ends of the member aren't moving. So we're just looking at what is it? It's the aspect of the axial force P. If we make a cut at some location along the member in the deformed configuration of the member, then we need some additional moment for equilibrium of P, in this case, times that delta to that particular cross-section where we're making the cut, or to the reference axis at that cross-section. So the P small delta part of the moment here is shown there in the second graph, and so the sum of those two effects gives us the total second-order moment, which in American practice we typically call M subscript U. So we need that maximum moment that's input to our design. And the result of this, you can say you can get this from a geometric nonlinear analysis if you're discussing it from a finite element perspective, or you can say you're doing a second-order analysis, which means equilibrium in the deformed geometry, right? You're evaluating equilibrium in the deformed geometry. Now, if we took a relatively deep dive into theory of elastic stability and started doing some derivations, we could show that the second-order deflection is approximated reasonably well by what we could get from a first-order deflection divided by 1 minus P over PE1, where PE1 is just the Euler load here. But the subscript 1 is a notation that the AISC standard uses to basically refer to a braced buckling load or a non-sway buckling load. If you see the subscript 1, that's non-sway. There's also an amplifier that we're going to talk about that's B1, that's for non-sway. If we consider even up to 95% of the Euler load, we're within 3% accuracy here in this particular case, and that's a generally accurate approximation for displacements or a number of other situations as well. So now, fairly basic manipulations here. We need the second order moment. Well, it's the first order moment plus P times the second order moment. Well, we got a problem in general for geometric nonlinear analysis. The deflection depends on the P delta effects, and the P delta effects depend on the deflection, right? And so the deflection, P delta deflection increases. If it keeps increasing, it's unstable. If it stabilizes to an equilibrium solution, then we basically can say that, delta first divided by 1 minus P over PE1. We multiply that by P, we've got our P small delta effect. So now you can kind of treat these notes a little bit like a very simplified textbook, if you wish. There's some algebra that I'm not going to waste your time just to plow through here in just a few seconds. But if we basically just manipulate that algebraically, we can get it to the form you see at the bottom of the screen. And the term in parentheses in the numerator, in AISC we call that term C subscript M. And the term in the denominator, again, that's 1 minus P over PE1. So that term in front of the M first, that's our B1 amplifier. If we have a first order analysis, we amplify the moments by B1 to get our estimate of the second order moments. Now, everywhere you see a red equation out here out to the right, that's basically referencing to the AISC standard, in this case Appendix 8 of the AISC standard. That's where that equation is coming from. And you have in the general information tab that was provided on the Google Drive, that's the PDF of the AISC specification and commentary are there for your ease of access. All right, so if we move that forward, we just did a fairly simple algebraic work here to write the B1 amplifier. Again, let's drill into C sub M a little bit further. And so again, that C sub M is 1 plus psi times P over PE1. Well, for this member that's subjected to uniform bending, we can calculate delta first without much trouble. That's ml squared over ADI. P1 is again pi squared EI over L squared. So let's put all the terms in there. We can see that the psi term for this case reduces to positive 0.23. Well, this is a little bit weird. The AISC specification actually, for a uniform bending case, suggests that you just take psi equal to 0. And if we look at every other standard in the world that I'm familiar with, that's if you have a uniform bending case, that's the way it's done. So you could argue that, that looks like we might have an approximation here. Now, from theory of elastic stability, the rigorous solution by Euler-Bernoulli beam theory is shown there, the secant pi over 2 times square root of P over PE1 times M first. If we compare to that, we can basically see that we've got anywhere from we've got basically a 15% error with this case that I'm showing you here. So that's a bit large. Of course, this is where we can wave our hands a bit and kind of wave it off. In design practice, have any of you ever designed a member in uniform bending? Would the end conditions be pinned? Probably the closest to this case might be if you have a strut. Maybe it's a WT section or something like that to gusset plates, and you're delivering the compression through the gusset plate. The gusset plate doesn't have much flexural stiffness compared to the members, so maybe you're getting close to a pin there. But even in that case, you're getting some restraint. So that's where we kind of wave our hands and say, okay, yeah, for this case, looks like that's maybe more error than usually we say we want to tolerate. But the codes commonly tolerate it for this particular case. And we use the approximation for uniform bending, where basically C sub M is equal to 1. Yeah.
So you're saying psi equal to 0 means you don't have any amplification?
No, so the psi equals 0 means, did I just?
Right.
Just back? Okay, good. All right, don't touch anything. So we're looking at the C sub m term there. So psi is the second in the second term on C sub m. So that's 0. C sub m goes to 1. And so then you've got your most basic amplifier 1 over 1 minus P over PE1, right? And so what I'm showing you here is that actually is can be 15% under predicting the theoretical value for this particular case. And you say, okay, can we wave our hands and kind of wave that off, right?
So also, doesn't this C sub m depend on the slenderness ratio of the beam?
It does.
Where does it come into picture?
That's coming in through the P over PE1. So the PE1 has the EI in it and the L.
Okay. And psi doesn't depend on that. Psi seems to be independent.
Correct. Yeah, we can see from our basic derivation we did, psi basically ends up being the form that I showed you here, there in the middle of the screen. Okay? All right, well, let's move to something maybe a little more interesting than just a uniform bending case. What if we have a simply supported member and it's subjected to transverse load? So these are two basic cases that show up in the commentary to the AISC specification. Uniformly distributed load with axial compression, a concentrated load at midspan with axial compression. So if we use that same development, very simple algebraic development, right? All we did is just said, okay, we need equilibrium in the deformed geometry. All right, so it's M first plus P delta, and then we put in some approximations for the amplification of the displacement. That got us to the psi formula, and if we put in the calculations for the deflections here, basically we go back to this middle equation here where we got positive 0.23 here for the uniform bending case. For the uniformly distributed load case, you actually do get psi equals 0 to maybe about three or four significant digits when you substitute into that. For the concentrated loading case, you get psi equals minus 0.2. This is what usually happens with most situations with the use of this formula for C sub m. You get a psi value that's negative, which means that your moment amplification then is not as severe as your displacement amplification. So other cases, we can use this same form, but here we essentially have to revert to, we can do the rigorous calculation from theory of elastic stability, and then we essentially can say, well, what psi value do we need in order to fit the results of the theory of elastic stability solution? And so there's a paper that's in the general materials that I've given you, and actually I think this is in the Module 1 section, that's from Iwankyu, that basically shows the development for these particular cases. So if you got a fixed beam, well, guess what? Your non-sway effective length factor for a perfect fixity at the ends is 0.5. And you get a psi of minus 0.4 for the uniform distributed loading. And in the other cases that I'm showing you here as well, the K1 and psi values, of course, for a propped cantilever, the effective length factor for the braced buckling with propped cantilever is 0.7. And so the only difference here, again, we still have the same form for C sub m. We have the psi value. The psi value there is basically a curve fit in this case. But PE1 has changed. PE1 is pi squared EI over KL squared. Now you might have noticed that I've got a star next to EI. That's because in the AISC specification, we have something that's called the direct analysis method, where we start playing games with reducing the stiffness to try to get a better calculation for what do we think the moments are in the physical structure. I'll say a little bit more about that as we're moving along, but it's really only the Americans that are doing that. The Eurocode is based more on an Ayrton-Perry approximation. We'll talk about what that is and how that works. So I'll kind of compare and contrast a bit, but I didn't want to come here and lecture to you, oh, here's how we do something in America, and that's nothing like what you do here in terms of the stiffness reduction. So a few things about that, why we think it's a good way to go in the Americas, but then I'll leave it there. And so the EI star, that's where sometimes, at least in the Americas, we will we'll implement a reduction on the bending rigidity as part of our elastic analysis calculations. All right, well those are great, but those are all just really ideal boundary conditions, all of those cases. So what do you do when you got something practical where it's not ideally fixed, it's not ideally pinned at the ends, it's connected to other stuff? You've got general transverse loads. The supports could be flexible. They're not necessarily rigid supports. In that case, if you try to derive or curve fit a psi value, you find you'll be very unsuccessful, because you'll find that the psi value just moves around all over the place, trying to curve fit something that's general like that. So what do we do practically speaking? Well, in many situations in civil engineering, bridges, buildings, we often don't have members that have huge p small delta effects. So we can get away with some very coarse approximations. And what's the coarse approximation? I'll just take C sub m equals 1. And so we basically apply an amplifier, B1, 1 over 1 minus P over PE1, the most basic amplifier in the world. Except PE1 here is given whatever connectivity you have to other elements your member or your element even is connected to here. If it's a non-sway case and you want to get an amplifier, okay, if you could calculate an effective length factor for those boundary conditions, and that gives you a little better result than if you just use the Euler load there for PE1.
So that's essentially the same factor you're using for the displacement?
The same as for the displacement, that's correct. That's correct. Let's look at a case that shows up a lot. I'm showing this member is kind of turned horizontal, but probably this shows up at least if we ignore the fact that I'm talking about pinned-in conditions right now. Multi-story buildings, we very typically have moment loadings that would look like this, right? Reverse curvature bending on the member. Well, in the AISC practice, given these first-order moments, where M2 is the larger first-order moment at, in this case, the right, shown at the right-hand end, M1 is the smaller moment. The question is, okay, well, we still have p small delta effects. For design, we need the maximum second-order moment, so label that. We call it MU when we go to our design equations. Well, we're going to use the same form, except this case gets a different C sub m factor. Now, one of the nice aspects that practically often happens when we have members like this, so generally we would say, oh, we need to calculate an amplification factor to evaluate okay, are we getting any larger moments between the ends? But practical cases, that amplifier often gives you a number that's less than 1, in which case what you're supposed to read into that is, oh, the M2 is your largest moment. The moment along the length that never gets larger than M2. If you do that calculation and you get a number less than 1. Always take B1 as 1, or if you get something larger than 1, okay, then the moment between the ends is larger, estimated. And the C sub m in this case, so this does show up in some of the Indian code equations, kind of in a more general context. In the U.S. practice, we use this as a reasonably good approximation for this particular loading with ideal pinned end conditions. And what we find with this is that it's a reasonably good approximation. It's a little conservative for combined large M1 and M2, so double curvature or reverse curvature bending and large PE1. But fairly adequate approximation. If we go back to the case I showed you earlier, in the limit that we're approaching uniform bending, we can be underestimating by as much as 15% at P over P1 of 0.7, which is why I picked 0.7. It's hard to get in a practical design a P over P1 on a member larger than 0.7. And so we do have that unconservative error in that particular case that we've already waved off, but otherwise it's a reasonable approximation. And then general in-restrained members. But so subjected to end moments, but we don't have any transverse loads between the ends of the member. We're moment connected to other framing. What do? Well, the generalization is similar to what I showed you earlier. Same form for the B1, same CM equation for this case, for just first order moment diagram. It's a linear variation in the moments along the length. But the P1 changes again. Given the end conditions, we can calculate an effective length factor. We'll look at some tools for doing that here a little bit later today, either computational or hand tools that we like in the Americas. So that's the general approach. Now, okay, lots of simple stuff, simple approximations to try to do practical design. But I want to show you next where there's really much more to the secondary interactions between adjacent members than these equations imply.